Hello, thank you all for joining my presentation on roadless volume calculations of Yavapai County. My name is Christopher Nevin McIntyre. I've been called Chris and Nevin throughout my stay at University of Arizona, but you can call me whatever you'd like. Not only am I a student, but I've been a GIS specialist at the city of Prescott for 4+ years now. I handle a wide variety of projects there, from utility networks and route optimization. So this calculation was not a request from Yavapai County or the city of Prescott. I just read about this metric and found it interesting, and I just thought it was valuable, and maybe hopefully you will too. So a little bit about the timeline and objectives of this presentation. I just want to give you an introduction to the study area, the distance to road grids and roadless volume. I want to go into the methods, what I did, the tools and the models, the calculations and visualizations as a result, and then just some discussion about uses and improvements. And then if we have time for a demonstration, we can, but it's not that important. It's not that great of a demonstration. So I know this is usually done at the end of a presentation, but I do want to acknowledge first the two articles that I read that kind of turned me on to this metric. The first is the original article of roadless space of the conterminous United States, published in 2007, and that's in, I think, Science magazine. They generated mean distance to road, DTR, and calculated RV per capita for the United States by patching together 30-meter resolution county level grids. Excuse me. They refer to this as the norm ED, which stands for National Overview Metrics Euclidean Distance. And you can view this data set, which is available from the USGS. Transportation Spatial Indicators was published in a book, Manual of Geographic Information Systems 2009 by the ASPRS. The article kind of dives a little bit deeper into the applications of RV and DTR. I can only find it in print format, but you might be able to find it online. But if you're interested in calculating these two metrics, I highly recommend that you look into those and read them. So let's start with the introduction. I apologize for the most boring slide of my presentation, but however, for non-Arizona residents and then also for non-Yavapai County residents, it's probably helpful. We're looking at 8,128 square miles of Yavapai County. Population was 235,000 in 2019, ranked 4 overall in Arizona. There's 27 cities, 18 wilderness areas, 2 interstates, 40 and 17, and then 7 US and state routes. A little bit more fun information, 8,128 square miles is larger than Connecticut, Delaware, Rhode Island, and New Jersey. It ranges in elevation from 1,900 feet to 8,000 feet on its mountain peaks. This includes vegetation types of grasslands, high deserts, pinyon juniper, ponderosa pine, chaparral, desert grassland, and shrub, you name it. 26% of this land is private, 38% is owned by the US Forest Service, 9% is owned by the BLM, and 27% is state of Arizona. Less than 0.5% is owned Indian reservations, very small amount. So an introduction to distance to road grids. I will often refer to it throughout this presentation as DTR. So that's what I'm saying when I say DTR. You can also think of it as Euclidean distance, and Euclidean distance is the tool that I used in Arcgis Pro to calculate this. So on the left is kind of the end result, right? What it looks like, depending on how you symbolize it. I chose this kind of elevation type symbology, which kind of shares a little bit of some colors together, but I still think it does the job. And you know what Euclidean distance is, a basic overview of it is basically calculating from source cell to destination cell. As you can see, let me get my pointer on here. So source being number 1, and to a destination, which is no value. And it's calculating basically the hypotenuse of this right triangle, right? And that's the true Euclidean distance. So roads are the source, and then non-roads are the destination. So next slide. Roadless volume is our fundamental measure of space between roads for this analysis. The effectiveness of roadless volume metric comes from its geometric behavior, right? Roads penetrating to the core of an otherwise roadless space reduces the volume much more than a road running alongside the perimeter of another road. So let's look at this first pyramid here. It's like a 1 kilometer by 1 kilometer square pyramid with a volume of 0.167 kilometers cubed. Now, if we look at this pyramid that's elongated, it's about the same, I guess, footprint area of the square pyramid, right? Because it's 3 by 0.333. However, it's 47% less volume because of the parallel roads running along the front, the north and south end there. So, and remember, height is determined by the Euclidean distance results, by what we saw in the DTR grid. So then the bottom pyramid, we're looking at just the generic, 1 kilometer squared pyramid there. If we dissect that into 4 separate, add 4 separate roads here, we're reducing it by half. However, if we just basically barely put a road along the edges here, we're reducing that by only like 13% or something like that, very little. So I want to go over what this analysis is and what this analysis isn't, because I think it's important. What it is, it's a way to illustrate tools that are useful in analyzing problems and then explore the reduction of roadless space. What it isn't is describing the relationship between roadless space and ecosystem services. If you want to know more about that relationship, we want to look into road ecology, right? And then this tool will be helpful in better understanding road ecology, and we can definitely use it in road ecology. Okay, so that basically does it for the introduction. We're now moving on to the methods here. The great thing about this analysis is that there's 2 data sources, and I love the simplicity of it, right? Because that's all you need. However, other things would be helpful, such as like reference data, city boundaries, labels, etc. In this map, we're looking at ADOT, Arizona Department of Transportation's linear referencing ADIS routes of 2019. That's the most recent data set I could find. And then we're looking also at the Yavapai County boundary here in the hatched here, and then also the extent of the data that we are going to be analyzing, which is a buffer of 30 kilometers outwards. And why we are including that is because we don't want no data cells along the edges, right? But we also want to capture any influence of roads, like maybe up here, that are running along just barely along the outside. So that could also influence basically the roadless volume that's inside of our boundary. Okay. And I did this, I calculated for like 11-year consecutive range using census data, tiger line shape files from 2010 to 2020, and then also this ADOT data set. And I'll explain a little bit why I included this ADOT data set a little bit later. So I can't move on without telling you that, like, don't make my mistake of just using data sets that you can find on the internet. Even though they are reliable sources, but you should really take time to, before you calculate a roadless volume, make sure you're choosing data sets that are going to help you, I guess, prove to have a beneficial or true or accurate analysis. And what, main things that you're looking for is like, are there missing roads? Are there gaps? Or is there incomplete roads? Accuracy and precision, 2 different things, obviously, and then, change over time. What you want to look for is like complete road networks, and city and county data does a really good job of this because, they use it for, routing in terms of 911 dispatch and whatnot, and they might have useful attributes such as paved versus non-paved, and it's nice and consistent. So moral of the story of this slide, we want to massage the data as much as we can if we can't find a real nice, reliable, and consistent data set. So there's 2 different models that I chose to make for this analysis, and I personally like to keep these models separate because I think the simplicity is better, right? I think in terms of keeping things separated, things like don't break as much, and that's a whole different topic we can talk about later. But anyways, the vector model is basically doing this. It's taking these 1, 2, 3, 4, 5, 6 data sets, it's merging them together, it's taking the boundary data, it's buffering it outwards by 30 kilometers, and then it's clipping to that. So now we have one full data set of all that all the roads of this study area buffered outwards. And, we can obviously clean up, including snapping roads or making sure that they're in the right place along the study area if you have the time to do that. Okay. And then the raster model. So basically this is the same, this is the same road network that we were looking at before. However, it's in raster now, it's in format. Here's the original boundary shapefile that we're gonna use for a mask. We're converting that to a DTR grid here using Euclidean distance. And then we're going to extract it by mask, which turns out to this. And then we're gonna calculate surface volume using the surface volume tool in Arcgis Pro, where roads are equal to 1, roads are our reference plane, and we're gonna calculate the volume above that reference plane. So you could see this is from the Esri documentation. This is our reference plane. Let's say that's a road, and then we're calculating the volume above it. And then we got to do our units. And then lastly, it's not included in this model here, but we could also apply a hillshade, which I have done in this presentation, and we will look into that later. But we can apply a hillshade to create this synthetic topography and kind of view the results visually. So this is the distance to road grids and maps that I made for this analysis. I've made a total of every year of this. The maps are displayed twice. Once as a minimum maximum symbology using a stretch type, that's on the left, and then secondly as classified values using a quantile method with 20 class breaks on the right. And the reason for that is because we can't view DTR at a single scale. It doesn't accurately display the data visually. So we needed to do 2 different maps to kind of show large scale and small scale. The small scale stretch symbology on the left here shows some of those high DTR values, right? And we can see that there's probably the highest is down here. You can see that, yeah, that's just how it's symbolized. So, and we'll get into what that area is a little bit later, and then the large scale maps on the right demonstrate the range. So as you can see, we have an extent indicator here. We couldn't really tell what that was, but now that we have it classified this way, we could see that there are some high values in there zoomed in. So like I said, I produced these maps from 2010 to 2020 using census data, and then also in 2019 using ADOT data. So this is the results of the surface volume tool in a table format, obviously. And unfortunately, the opposite of what I expected happened. And this kind of goes back to the data maintenance slide that I talked about a little while ago. As time increases, I think we should expect a loss in RV. However, RV increased. And I think, it's a safe assumption to say, like, as time increases, more roads are built and faster than they are removed. So usually that's a safe assumption to make that, we would lose RV. Unfortunately, it didn't happen. So the census data set did not prove to be a kind of a reliable from a temporal standpoint at this county level scale for the time span of the analysis. However, it still can be used in smaller scales, right, to kind of visually see the changes in urban areas or even rural areas. And so that's why I decided to include this ADOT data set here, so we can really see the changes on how much was decreased. And I have it from comparing it from 2010 and then the previous year. And then keep in mind, ADOT is comparing from 2019 to 2018, which is that 11% decrease there. So here's the results of like applying a hillshade to that DTR map, and it kind of shows you this synthetic topography. Where summits are the local maxima for the DTR values. Once again, you can see these large summits here, and then inside the smaller areas at a larger scale, you can have the roads at 0 pseudo elevation. Just as a side mention, I use the raster hillshade function in my analysis instead of the other different hillshades that are available in Arcgis Pro. And I should probably investigate the reason for this, but for some reason, the raster hillshade function produced a clearer, more visually clear map. So this is a I'm gonna push play here, and let's see, maybe I switched my pointer and we can maybe I have to, oh, here we go. So this is just a video showing the change over time, and I know it's a lot to view visually. Your brain might not be able to process all that information changing at once, but over time you can see how roadless volume changes, right? And then I did it at a larger scale, so you could see, like, in terms of city limits, how that changes, and you can, yeah, over time you can view this. One thing, if I can get control of it here, one thing that you can do, oops, is you could pause it and view the changes as like a slide here. So we could see that big reduction or that big gain in RV in 2018 to 2019, which is unexpected in those two areas there, right? Like we see a huge gain, which we can investigate that further, but it's just something to realize. And then obviously the A dot there where it's showing a lot of less maximum values. So let's talk about a little bit about the applications. I'm going to speed this up because I only have a minute left, but some things that you could do. One thing that we already viewed is change over time. From a development perspective, development planners could use this to plan construction while minimizing road volume reduction. We could symbolize and view the most remote areas based on distance to road. We can use it in habitat modeling, such as weighted sums and weighted overlays, and then we can model remoteness as a travel time. And there's probably other applications as well. So you're probably wondering what that area was over there that had the highest DTR values, and that's part of the Mizatzel Wilderness area right there. And that's, but you know, keep in mind, look at this Wet Beaver Creek Wilderness area where there's actually some outside of it. And if you're not familiar with what a wilderness area is, they are designated by the Wilderness Act of 1964, which road building, motorized vehicles, and mechanized vehicles are prohibited. So that's, you would expect that's where the highest DTR values would be. So some improvements that we could do towards this analysis is that we could actually just use paved roads. My data set's probably used everything. So paved and non-paved, you name it. So I think paved roads would probably make this analysis a little bit more honed down and focused, right? However, with that being said, there's probably some non-paved roads that where there is high traffic. We could also include traffic. We could also include road width. We could also do lighting and noise. And how we could maybe incorporate that is just basically, depending on the road bounded polygons, we can kind of weight those differently to reduce or add to volume contributions. I don't have time for a demonstration, so we'll just open it up for discussion and questions at this point.